Okay, so moving on to a chemical formula. Okay, I'll just briefly explain the features of a chemical formula. Okay, so here is an example, right? C3H8O. Okay, so these chemical symbols, for example, C is a chemical symbol. Okay, it represents okay, what elements are present, okay, inside this compound. So this whole molecule here, this C3H8O, this entire molecule here, okay, is a compound. All right, and the symbol C, H, and O represents that the element carbon. C represents the element carbon, right? It's a symbol for carbon. Okay, the element carbon. H is the symbol for the element hydrogen, okay, and O is the symbol for the element oxygen. So what these symbols C, H, and O represent, okay, is that the elements carbon, hydrogen, and oxygen are present in this compound. Okay, so what about these numbers over here? Okay, these numbers are called subscripts, right? And what these numbers represent is they indicate how many of such atoms are present in this compound, right? So C3, okay, represents that there are 3 carbon atoms present, okay, in this compound. H8 represents that there are 8 hydrogen atoms present in this compound, and if there's nothing here, it means that there's 1 oxygen atom present in the compound. Nothing means 1. Okay, so no subscript indicates that there's only 1 of such an atom, right, in the compound. State symbols. Okay, what are state symbols? State symbols basically tell you the, as the name suggests, the states of the substances. All right, so solid is represented by S, liquid is represented by L, gas is represented by G. Okay, that's quite straightforward. Okay, one sort of like more counterintuitive one will be this term aqueous. Okay, aqueous is represented by the symbol AQ. Right? What aqueous actually means is that basically the substance is soluble in water. Right? So when you see the state symbol AQ, okay, it means that the substance is being dissolved in water. Okay, and what happens when they dissolve in water? Okay, they actually split into ions. Right, so they are soluble in water, and when they dissolve in water, they split into ions. So actually, when you see a compound that's has the state symbol AQ, okay, which means that it is in the aqueous state, okay, it means that the substance has dissolved in water and has split into its respective ions, okay, upon dissolving in water. Okay, so here we'll finally see, okay, how valency actually is useful in helping us to write a chemical formula, right? So let's just take a look at this example, okay, of K2O. Okay, how do we, okay, this is actually potassium oxide, right? K represents potassium, O represents oxygen. So the name of the substance is actually potassium oxide. Okay, we call that the metal, okay, which is potassium. Okay, the name remains unchanged. For oxygen, which is the non-metal, okay, it's written behind the metal, and it ends with IDE. So the name of this substance is actually potassium oxide. Okay, so how do we know that the chemical formula is actually K2O? How do we know that it's actually a 2 here? Correct? How do we know that there's a 2 over here, whereby there are 2 potassium atoms and 1 oxygen atom inside, okay, within the compound potassium oxide, right? So to determine what is the subscript over here, we will have to look at the valency of each of the elements, right? So potassium, for example, is in group 1, so we know that it has a valency of 1. Oxygen is in group 2, so it has a valency of 2. Okay, so potassium has a valency of 1, oxygen has a valency of 2. Okay, we can deduce this from their group numbers. Okay, so recall that above we have learned how to deduce valency based on the group numbers of the elements. So what you do is you actually do a cross method or swap method whereby you swap the valencies, right? So if potassium has a valency of 1, you swap it with oxygen. Oxygen has a valency of 2, you swap it with potassium, right? So after you swap it, okay, that will actually give you the ratio of the atoms, the number of atoms within the compound, right? So because here after you swap it, the valency numbers, okay, K will have 2, O will have 1. So basically there are 2 K atoms and 1 O atom inside potassium oxide. So it will be K2O, right? This step here, divide, is simply just saying that you have to, okay, so first you swap and then you divide, right? So divide basically just means you have to reduce it to its, okay, if there's a common factor, you just have to divide it, right? So reduce it to its lowest form, right? So if it's 2:1, okay, there's no common factor, so it is basically in its lowest form, so it's just 2:1, right? You don't have to do anything or any division. This is for monoatomic, okay, whereby it's K and O. What happens if you have polyatomic, whereby, for example, you have NO3, okay, nitrate ion, okay, a polyatomic ion. Same method, right? Okay, same thing, you have the valency, okay, Ca, calcium is in group 2, so valency of 2. Nitrate ion, okay, based on the table they have given you, okay, it has a valency of 1. Okay, so what you do is you swap, okay, so 1 and 2, so 1 calcium, 2 nitrate ions, divide, it's already in the lowest form, so there's no need to do any further division or simplification. So there will be, okay, 1 calcium atom and 2 nitrate, okay, ions, okay, present within calcium, the compound calcium nitrate, right? Okay, so it's CaNO3 2. One important point to note is that for polyatomic ion, okay, if there is, for example, several of them, maybe there are 2 of such ions, okay, within the compound, you must put a bracket to indicate that this NO3 is one, collectively they are considered as one polyatomic ion, and there are 2 of such polyatomic ions. So there are 2 of such NO3, okay, 2 of such NO3, which is nitrate ions, okay, therefore the bracket must be around the entire NO3, okay, to show that there are 2 NO3 or nitrate ions. Okay, so how do we write actually chemical equations, right? So this is a chemical formula of the substances, right? Now we'll actually go into a chemical equation, okay, which shows what it actually means is that you have several substances, okay, reacting with each other, okay, to give, okay, maybe a different set of products, for example, right? And in showing this reaction, okay, you need to represent this reaction in the form of a chemical equation, right? So a chemical formula represents the individual reactants, okay, or the products, right? Whereas the whole chemical equation shows how the reactants react together to form the products. Okay, so that is the difference between the two. So how do you write a chemical equation is that the reactants, which is the atoms before the reaction, okay, must be balanced with the, okay, number of atoms, okay, after the reaction, right? So the atoms, number of atoms before must be equal to the number of atoms after, okay, it must be balanced, okay, the atoms cannot disappear, okay, from the reaction, right? They must be present before and after the reaction. So you place a number in order to balance, okay, you place a number called a coefficient, right? Okay, in front of the chemical formula. Okay, basically you add in numbers in front of them of the substances, okay, or the chemical formula of the substances, to show that there's like different numbers of such substances, so as to allow the overall equation to be balanced, right? Okay, and when the coefficient is 1, there's no need to write it. Okay, so I think it's better illustrated in the form of an example. Okay, so for example, if let's say I have an equation, okay, the equation basically is that you are given that, okay, hydrogen reacts with nitrogen Okay, so the reactants are hydrogen, okay, and nitrogen. Okay, note that hydrogen usually exists as a gas, okay, and because it exists as a gas, it is usually diatomic. Diatomic means di represents two, so there are two atoms, two hydrogen atoms, right, in one molecule, one hydrogen molecule, right? So H2, when they tell you hydrogen, okay, reacts with nitrogen, okay, the reactants will be hydrogen gas, which is H2, okay, diatomic, and nitrogen will also be in the form of nitrogen gas, okay, and it will also be diatomic. So hydrogen H2 and nitrogen N2, they are the reactants. Okay, the reactants are before the arrow. Okay, to form ammonia. So ammonia is the product. Okay, ammonia, you have to know that it's actually NH3. Okay, so ammonia is actually NH3, whereby there's one nitrogen atom and three hydrogen atoms. Okay, inside within one molecule of ammonia. You have to know that. Okay, so ammonia is the product, right? So here, as you can see, this is wrong. This is unbalanced. Why? Because the number of hydrogen and nitrogen atoms before and after the reaction is not conserved, right? What this means is that if you can see, before the reaction, there are two hydrogen atoms and two nitrogen atoms, but after the reaction, there's only one nitrogen atom and three hydrogen atoms. So as you can see, before there's two hydrogen, after there's three hydrogen, so it's not balanced. Before there's two nitrogen atoms, after there's one nitrogen atom, it's not balanced, it's not the same. Okay, so this is wrong, right? Wrong. Okay, so how do you actually balance it? You actually have to add numbers, they call it coefficients, in front of the chemical formulas to try to balance the number of atoms, right? So in this case, you add a 3 in front of the hydrogen, okay, the nitrogen remains the same, and you add a 2 in front of NH3. Okay, why? Because in doing so, before the reaction, you have 3 of H2. Okay, so basically you have a total of, okay, so one molecule of hydrogen gas, which is H2, consists of 2 hydrogen atoms, and if there's 3 of such hydrogen molecules, there will be 3 times 2 to give you a total of 6 hydrogen atoms, right? And over here, if there's 2 NH3, okay, it means that the number of hydrogen atoms will be H3 times 2, right? Because in one molecule of ammonia, NH3, there's 3 hydrogen atoms. So if there's 2 of them, okay, the number of hydrogen atoms will multiply by 2 as well, right? So if there's 3 hydrogen atoms in one molecule, there will be 6 hydrogen atoms in 2 molecules, right? So after, there's also 6 hydrogen, so it's balanced, right? So before that, there's 2 nitrogen, okay, N2 represents there's 2. After, there's also 2N, right? So NH3, there's 1 nitrogen, but there's 2 molecules of ammonia, okay, so total there are 2 nitrogen atoms, right? So the number of atoms before and after are balanced and conserved, okay, which means that they are the same, okay, and therefore this equation is balanced and is correct. Okay, so here just a summary of the steps to writing the chemical equation. Okay, so usually the question will give you, okay, a reaction in the form of sort of like a word form. Okay, so they'll tell you that sodium reacts with zinc nitrate. Okay, so you have to write down the names of the reactants and products, right? So reaction between sodium and zinc nitrate, which means that sodium and zinc nitrate are the reactants. Okay, so you write them on the left hand side. And what are the products? Okay, you will learn subsequently more about how the chemical compounds react to form products. Okay, but in this case, just know that it is enough to know that the sodium will actually kick the zinc out. Okay, it will actually replace the zinc, okay, from the nitrate. Okay, so it will actually form sodium nitrate, okay, and zinc will be kicked out of the, okay, this is called salt. Okay, so zinc nitrate, the element zinc, okay, the ion zinc will actually be kicked out of the zinc nitrate salt to form, okay, zinc in its pure elemental form. Okay, so this is the basically the the whole equation in its word form. Okay, sodium will react with zinc nitrate to form, so these are the reactants to form sodium nitrate and zinc as products, right? So once you have gotten the chemical equation in the word form, okay, the next step will be to replace these words with the chemical formula, right? Using the valency method to determine how many atoms are there, okay, within, or how many ions are there, okay, within the substance itself, right? So sodium is basically just sodium. Sodium metal is just Na, okay. No, it's just sodium, very simple. Zinc will be zinc, okay. Sodium nitrate, okay. Sodium is the metal, so it's written in front, no change to its name, okay. Nitrate will be as given in the table above, okay. It is a polyatomic ion, nitrate, and the name of it, okay, of the nitrate ion, okay, it actually its chemical formula will actually be NO3 minus, okay. So based on this charge, because nitrate has a NO3, okay, minus charge, so in this case, okay, nitrate actually is actually NO3, okay, minus, okay. So what it actually has is that, okay, it has a valency of 1. Alright, sodium actually is a metal, okay. It actually exists as Na plus because it is in group 1, so it has a valency of 1, right? So this is sodium is because it is in group 1, so you know that it has a +1 charge, and therefore it has a valency of 1. Nitric ion is given in the table, it has an overall charge of -1, okay, so its valency is also 1. So when I actually cross it, okay, it will still be 1, 1, okay, and therefore it is just NaNO3. Right? Yeah, so that's why we have the chemical formula for sodium nitrate as NaNO3. There's 1 Na and 1 NO3. Okay. So what about zinc nitrate? Okay, so okay, zinc nitrate. Okay, what we have for zinc nitrate will be, okay, we know that zinc is a transition metal, okay, as you can recall, so it is not in any of the, you can't actually tell its valency from the group number, so because it has a variable oxidation states, okay, so, but just know that zinc commonly exists as zinc 2 plus, okay, so its valency is 2, okay. As given above, okay, I have sort of like highlighted that zinc usually exists as a zinc 2 plus ion, and it usually has a valency of 2. Okay, and NO3 minus, we have found that just now I've already explained that in the table it has a -1 charge, right? It's a polyatomic ion with a -1 charge, so valency is 1. So if I swap it, okay, I do the cross method, okay, so what I will get is I will have 1 zinc, so Zn, and 2 nitrate ions, so 2 of such nitrate ions, so it's NO3, 2. But remember to put a bracket because there's 2 of such nitrate ions, so the entire, you have to actually put a bracket to show that this subscript 2 applies to 2 of the entire nitrate ion. Okay, this whole polyatomic ion, there's 2 of them, right? So what do we do next? Okay, we will balance the equation by writing numbers in front. Okay, so here there is, we can see that here there will be, in the reactants there's 2 of such nitrate ions. Okay, so after that, because it is NaNO3, there's only 1 nitrate ion here, so in order for there to have 2 nitrate ions after, I need to add a 2 in front here, right, so that the NO3 will be balanced, right? So before there's NO3 2, there's 2 nitrate ions. After, I add a 2 in front of the NaNO3 such that there will be 2 nitrate ions as well. So the nitrate ions are balanced. Okay, and because of these 2 here, okay, now I'll have 2 Na, 2 sodium. So over here, previously there's only 1 sodium, I have to add a 2 sodium over here to balance out the sodium with the 2 sodium over here. So now there's 2 sodium here and 2 sodium here. So the sodium before and after is number of sodium atoms are balanced. Zinc, there's 1 zinc over here, and here it will remain as 1 zinc, so it's also balanced. Okay, so yeah, by adding this coefficient 2 here and this 2 here, okay, we actually balance the equation. Last but not least, include the state symbols. Okay, so sodium metal is usually solid. Okay, zinc nitrate can actually dissolve in water. Okay, so it will be aqueous form. Okay, sodium nitrate will also be soluble in water, and zinc metal is a solid. Okay, metals are usually solids. So and then we have completed the chemical equation. Just take note that the solubility of compounds, okay, will be further elaborated on in subsequent topic. Okay, so for now, just know that these two compounds are soluble, and hence we put the aqueous state symbol behind them. Okay, so ionic equations. All right, how do we actually write ionic equations? Okay, so ionic equations is actually the same as chemical equations. You just have to do an extra step of cancelling away the spectator ions, right? So they're actually a simpler form in that you just do an extra step of cancelling away spectator ions, which are ions that are not involved in the reaction, right? So you do not include those ions that are not involved in the reaction, right? So how do we actually do that? Okay, let's just use the same example of this. Okay, so as constructed above, we have this chemical equation over here. Okay, we'll use this chemical equation over here. Alright, and we'll just write this here. So how do we actually construct an ionic equation, okay, from here, right? So what we do is we actually what we can do is, remember when just now I briefly explained in the aqueous state, okay, when they actually dissolve in water, they will actually split. This compound actually splits into its respective ions, right? So what we do is we actually do the splitting, okay, of everything that is in the aqueous state. Okay, so as you can see, okay, the solid remains the same, 2NaS solid remains the same, but the zinc, because in aqueous form, we split it to its respective ions, so zinc will be 2+, okay, as I explained above. Okay, zinc usually exists with a valency of 2 and has a 2+ charge, so zinc will be Zn2+ equals NO3 minus, because there's 2 of it here in the subscript, so there's 2 of such nitrate ions. Okay, and for here NaNO3, okay, we also, because it's aqueous state as well, we also have to split them into its respective ions. So there's 2Na plus, okay, and there's also 2NO3 minus. Okay, the coefficient 2, okay, in front applies because there's 2 of such NaNO3, okay, this substance, 2 of this substance, okay, and each molecule of this substance has 1 sodium and 1 nitrate. So 2 molecules of this will have 2 molecules of sodium, Na, and as 2 molecules as well as 2 molecules of nitrate ions. Okay, so the 2 applies to both the Na and the NO3. Right? Zn remains the same because it's not aqueous form. So what we can do here is that this, if you can see, okay, we cancel away, okay, those ions that are present on both sides, okay, before and after, they are the same, right? So if they remain the same before and after the reaction, okay, it means that they do not participate in the reaction, okay, and therefore they are spectator ions, right? So we cancel away those that remain the same. So as you can see, NO3 aqueous and NO3 aqueous remains the same, so we cancel it out, right? So we cancel out this, we cancel out the NO3. Zinc, actually there's a change, okay, it changes from the aqueous state. As you can see, zinc changes from the aqueous state to the solid state. So zinc actually participates in the reaction, right? There's a change, right? And from sodium solid to sodium aqueous, there's also a change, right? From solid to aqueous, okay? So sodium, there's a change to the sodium, and therefore it participated in the reaction. So we do not cancel away sodium and zinc because they experience and undergoes a change in the reaction, and therefore they participated, so we do not cancel them out. Okay, it's only the nitrate ions, okay, whereby there's no change, okay, the state symbols are both aqueous before and after, and there's no change to chemical formula whatsoever. So we can cancel them out because they are spectator ions that do not participate in the reaction and remain unchanged. Okay, so they have the same, okay, chemical formula, charge and state before and after the reaction, right? So anything that has the same chemical formula, charge and state, okay, before and after, we can cancel them away. So removing these two, okay, the final ionic equation will be, okay, we have sodium over here, okay, meaning unchanged, Zn2 plus aqueous, okay, which is over here, right, Na2 plus, which is over here, and Zn solid will be over here, right? Okay, so basically we just remove the spectator ion, which is the nitrate ions.